In this tutorial, we share a style for RailClone to help create cupboards and kitchen units. In the first half, we'll take a detailed look at a style supplied in the downloads, showing you how you can change door types and the hanging direction just by making simple changes to the base spline. This is ideal for quickly creating kitchen layouts, and best of all, this style is easy to reuse, so once you've understood it, you should only have to swap the geometry for any new kitchen or other types of cupboards that you want to create. In the second half, which is aimed at advanced users, we'll take a closer look at how to create a style like this from scratch, including the strategy of breaking down a style into several interdependent generators, a common approach for more complex projects. You may never need to actually create this style from scratch. Instead, I'll demonstrate how it works and show you how you can adapt it for your own needs by preparing and swapping the geometry as required. Let's start by looking at the basics of how to use the style to create a simple kitchen layout. So the entire object is driven by a single spline. By editing the spline's material ID, line and vertex types, you can control many aspects of the design. There are also settings found in the parameters rollout of the modify panel. The height of the worktop and the cabinets is derived automatically from the doors, so if you change the door segments, the rest of the style updates automatically. Doors themselves are created by adding vertices. One single door is scaled automatically between two vertices. Doors are sliced so that only the midsection scales, minimising the chance of incorrect deformation on the sides. And different types of door are selected by changing the material ID on the spline segment. As you change the ID, you'll see the type of door updates in real time, so you can quickly lay out your kitchen design. To change the hanging direction of a door, you just change the type of the vertex preceding the section. A corner vertex has the door hanging from the left, and a corner Bezier vertex hangs the door from the right. If there is a change in cupboard height, for example when you want a worktop height and a larder height cupboard on the same spline, you'll just need to break the vertex at the point where the change happens. This is so that the height of the cabinet's sides can be recalculated for the larger door and continue past the height of the worktop. And of course, sometimes you may not even want a worktop on top of the cupboards, especially for larders or if you're using the style for wall cupboards. In this case, you can turn off the worktop by selecting the spline segments, then right-clicking and changing the type to curve. And that just about covers the parts of the style that can be modified using the spline itself, but there are also a number of useful parameters found in the modify panel. The first of these is the Y size parameter that's used to adjust the depth of the cupboards. Everything is linked to this, so when it's changed it affects the cupboards, door position, plinths and cabinets. The height of the plinth can also be adjusted independently using the plinth height parameter. As you can see, when this is adjusted, everything above is also moved. Plinth offset is used to push the plinth backwards underneath the cabinet, and plinth end padding lets you choose if this effect should also be applied to the ends. The worktop overhang is used to extend the worktop over the cabinets. You can also, if you want, use a negative value to reverse the effect. And finally, door padding can be used to adjust the gap surrounding the doors. When combined with door offset, you can also use this parameter to decide if the door is housed inside the frame or mounted on the face of the cabinet. So as you can see, the style is relatively easy to use, and now that you understand it, let's take a look at how you can use your own geometry. The various elements have to be prepared in a particular way, but it's no more complicated than slicing your pre-modeled doors and other parts into sections so they can be easily scaled to different sizes. Normally, for example, to build a kitchen you'd need all your different doors and carcasses in different widths, but using this style you need just one for each type of door or drawer combination. So looking at the types of the geometry that you can change if you want, we'll start at the bottom and look at the plinth, which is divided into three parts: a side, a corner and the front. Working upwards on top of this, the cabinet itself is also divided into three parts, which is just the bottom, the sides which are mirrored, and the back. If necessary, you could also add the top of the cabinet as an extra segment, but in my example and the files in the download for this tutorial, I'm simply reusing the bottom for the top. Continuing upwards, on top of this, the worktop is just a simple single section. There's nothing special here. And then finally, we have the doors. These probably involve the most work because we need to separate them into those parts that can be stretched on the x-axis and those that must remain the same size to avoid distortion. This usually involves splitting them into three pieces, with two fixed size sides and a third section in the middle that stretches to fill the available space. Any handles on the doors should be placed on the right hand segment, as you can see. That is, except for handles that should be in the centre of the door. These will need to be separate objects, and the pivot should be aligned so that when it's placed at the bottom of the door, the handles are in the correct place on the Z axis. And this is all you need to create a flexible kitchen style using this RailClone object. To add these pieces to the RailClone style, you'd need to do the following. Open the style editor and don't panic. If you're not experienced with RailClone, this graph can look a bit daunting, but there's no need to be worried. You only need to locate and change the orange segment nodes that look like this. They would normally feature the name of the geometry selected from the scene as a title. It's most likely it's the doors you'll want to change, so to do this, locate the cluster of segment nodes attached to 3 selectors called door left, door default and door right. These segments relate to the door pieces we just saw, and the order that they're connected to the selector operators determines the material ID used to assign them to a spline section. So starting at the top of the selector list, the material IDs increase for each additional connection. So in this graph, at the moment, there are 8 different door types that can be selected. That's not a limit though. To add more, you just need to connect additional segments. As an example, let's add this drawline door so that it is selected using material ID 1. Remember that it's made of 3 parts, actually 4 if you include the centered handle. So select the first segment node connected to the selector operator called door left. Then go to the properties panel. Click the object picker button and then select door draw line left from the scene. Now you need to do basically the same for the other 2 selectors, making sure that the same input is used in each one so that the IDs will match. So first we'll select the first segment node connected to the selector operator called door default, go to the properties panel, click the object picker button and select draw line default from the scene. And then select the first segment node connected to the selector operator called door right, go to the properties panel, click the object picker button and pick door draw line right from the scene. And then you just keep following this procedure to add any additional doors. Once you've done this, you can check the style by applying it to a spline and changing the material ID. Each change should show you a different door. When a door also needs centered handles, as in this case, these are added separately. Find the selector operator called centered handles and there should be the same number of inputs as we saw with the door selectors. This is because each one of these corresponds to the same material ID. Even if no handle is required, it's important to add a null segment so that the number of inputs remains exactly the same. So the doors are probably the most important, but it's also possible to change the other geometry elements. For example, you could change the worktop just by finding the segment with the same name and picking your geometry from the scene. Or to change the cabinet, you'd find frame back, frame side and frame bottom and pick those from the scene. And finally, to change the plinth, just look for the segment nodes called plinth side, plinth top and plinth corner. And then you can pick those from the scene. And in this way you can quickly build a completely different style. By adding or changing these segments, you should be able to create a wide range of cabinet and door types. But in the next section we'll learn how to create this style for yourself from scratch for a deeper understanding of RailClone. I should warn you that this section assumes a certain amount of knowledge of RailClone, and if you're new to the plugin you should try some of our beginners or intermediate tutorials first. For advanced users who'd like to build a style like this from scratch, I'll now demonstrate how that's done. The focus here is on the creation of several different but interconnected generators to create a style that adapts to the segments and base objects added to it. Also, almost all of the dimension values are extracted automatically from the segments, so that the style can be really easily updated, either using parameters or by adding new geometry as we've seen. We'll start at the bottom with the plinth. There's already a RailClone object in the scene we can use for this exercise. It's largely empty except for the segments which have been added to save a little time later. These will use their default settings, except that alignment Y has been changed to top to make sure it aligns with the base spline correctly, as we'll see. So we'll start with a new A2S generator. It needs a spline, so create a new spline node, pick a test spline from the scene and wire it to the generator's X spline input. We'll set the depth of the cabinet to the Y size using a parameter. To do this, right click on the generator and export the Y size property. Then create a new numeric node and wire it to the exported Y size property. Change the numeric node's mode to scene units. Go into the generator's properties and set the default mode to scale. This is so that the plinth segment will stretch along the path of the spline without getting sliced. You should also change bevel mode to none to prevent the spline being sliced every time there's a vertex. This will maximise the amount of instancing that takes place as slice segments render a static geometry. Now we're ready to add the geometry. Wire the plinth side segment to the generator's left input. Also, wire it to the right input via a new mirror operator. Wire the plinth top to the generator's bottom input, and wire the plinth corner segment to the generator's left bottom input, and then wire it to the right bottom corner input using another mirror operator. We now have the basic plinth working, but we'd also like to add a parameter to control the height. To do this, click on each of the plinth segments in turn and export the Z fixed size parameter. Wire these newly exported parameters to a new numeric node and call it plinth height. Once again, change the type to scene units. Ideally, we'd like the spline for this style to be at the back of the cabinet, near the wall. At the moment, as you can see, the spline is at the front. To fix this, we'd need to negatively offset the geometry on the y-axis the same distance as the y size. To do that, export the generator's y offset parameter. Now somehow we need to return the negative of the output from the y size node. The way to do this with the fewest nodes in the graph is to add an arithmetic operator, change the mode to expression, and enter negative input 1 into the expressions editor. Now you can wire the y offset node to the arithmetic node and then wire the arithmetic node to the generator's exported y offset input. If you get an error message at this point, don't worry. It can be ignored because you're not using any incompatible features and it'll work fine. Once you've done this, you can now adjust the depth of the plinth from the modify panel, and the back of the plinth will always be aligned with the spline. To make the style even a little more flexible, we also want the ability to offset the plinth so that it's stepped in from the cupboard front. In this setup, the Y size will set the cabinet depth and then we'll deduct from this a plinth offset. To do this, create another numeric node and set the type to scene units. Name this node plinth offset. Create a new arithmetic node and set the mode to subtract. Wire Y size to the first input and plinth offset to the second input. Wire the new arithmetic node to the generator's Y size input and the Y offset via the existing arithmetic node. Nearly there. Now we have the padding, we want to provide an option to add it to the ends of the generator too. To do this, we need another numeric node to act as a toggle to turn this feature on and off. So we can create a new numeric operator and set the mode to Boolean. You can call this node something like plinth end padding. Then wire plinth end padding to another new arithmetic node and change the mode to expression. We're going to create a condition, so open the expressions editor and enter if, open brackets, input 1 equals 1, comma, input 2, comma, 0, close brackets. Then wire the plinth offset node to input 2. In English, this expression is saying, if the plinth end padding is turned on, return the value from input 2, which is the plinth offset numeric node. Otherwise, just output a value of 0. With that done, select the generator and export the padding start and padding end limits parameters. Wire this new conditional arithmetic node to these two inputs, and now you can toggle on and off the end padding, adjust the width, adjust the plinth offset, and change the height. So in the next step, we'll start building the cabinet carcass. To create the cabinet, we begin with the base, which should sit on top of the plinth we just created. To do this, we'll start with a new, separate L1S generator. As I mentioned, breaking things down is the easiest approach with this kind of object. So first of all, create the new L1S generator and wire the existing spline node to the generator's spline input. We want to change the default mode to scale, for the same reasons as we discussed earlier, and we want to change bevel mode to none. Wire the frame bottom segment to the default input. And we want to adjust the depth of this cabinet, so export the Y fixed size property of this segment and connect the Y fixed size numeric node that's already in the graph. And then finally, the cabinet bottom is currently sat on the floor intersecting the plinth, and we want it sat on top. So to do this, we need to adjust the Z offset parameter of the generator. So right click on the generator and export the Z offset parameter. and then wire the plinth height numeric node to the Z offset input. And now, as you can see, if you adjust the height of the plinth, the cabinet bottom also moves up accordingly. So with the bottom side done, we can add the back and the sides of the cabinets. And to do this, we'll just duplicate the L1S generator we just created and remove the existing segments from the inputs. We're then going to wire a transform operator to the start, the corner and the end inputs. This is so that we can control the height of the cabinet based on the size of the other segments in the style. So right click on the transform operator and export the Z fixed size and Y fixed size parameters. We should also export the X size attribute because we'll use it later to create padding for the doors. Then connect the frame side segment to this transform operator. And to adjust the depth of the cabinet, connect the Y fixed size numeric node to the Y fixed size input. In this style, I've imagined the cabinet height will be automatically calculated based on the size of the door segments that are added to it. So to do this, find the existing door default selector operator. It's up the top here. Right click on it and export the Z size attribute. This will allow the height of the currently selected door to be piped in to drive the height of the cabinet. Then create a new arithmetic operator and wire this Z size attribute to the first input. Wire the arithmetic operator to the Z fixed size input of the transform operator we just created. This arithmetic operator allows us to adjust the padding of the door. So to do this, add a new numeric node, set the mode to scene units and wire it to the arithmetic operator twice. Why twice, you might wonder? Well, this is because you're going to be adding padding to the top and the bottom of the door, so we need to double the value. And that takes care of the sides. Now let's add the back. Wire a new transform operator to the default input. Right click on the transform operator and export the Z fixed size parameter. And then wire the same arithmetic operator being used to control the height of the sides to the Z fixed size parameter of this node. Now both segments are deriving their heights from the doors. And then finally, we need the sides to start on top of the cabinet base, so again we need to offset the Z axis. The correct offset value should be the sum of the height of the plinth plus the thickness of the base. So to calculate this, create another arithmetic node and wire the frame bottom segment's Z size attribute plus the plinth height numeric node to its inputs, and then wire the arithmetic node to the generator's Z offset input. With that done, we're ready to add the top to this cabinet. So to add the top, duplicate the L1S generator we just created and remove the existing segments from the inputs again. Wire a transform operator to the default input. Right click on the transform operator and export the Z fixed translation parameters. We're going to use this instead of the generator's Z offset parameter to position the worktop. There's a good reason. The generator's property offsets all segments in the style and must be the same for all the spline sections, whereas the translation values for individual segments allow you to adjust the height at any point. This means you can have cabinets of different heights on the same spline. With that done, wire the frame bottom segment to the default input. And then to set the position on the Z axis, we need to add together the height of the plinth, the height of the cabinet base and the height of the sides. To do this, we'll create another arithmetic node and attach the node driving the height of the previous generator and then the existing arithmetic node that's being used to drive the height of the doors. And that's the cabinets done, so let's add the worktop on top of this. The worktop is pretty straightforward, but it has one unique feature. The worktop should only appear where the segment's type is a line and not a curve. And to achieve this, we will once again duplicate one of the L1S generators and remove the existing segments from the inputs. And then wire a conditional operator to the default input. We'll use this to detect the type of spline. Open this node's parameters and turn on type, and then change the drop-down menu to line. With this done, when the spline is a line, it will return the segment wired to the true input, and when it's a curve, it will return the segment wired to the false input. So we'll wire a transform segment to the true input. Just like the cabinet top, we'll use this instead of the generator's Z offset parameter to position the worktop on the Z axis. Right click on this and export the Z fixed translation parameter. Now let's create the sum for this value. Create a new arithmetic node and wire the frame bottom segments Z size output and the node driving the height of the cabinet top segments to the inputs. The order isn't important. Wire the new arithmetic node to the Z fixed translation input of the transform operator, and the height is now set correctly. Wire the worktop segment to the transform operator. Right click on it and export the Y fixed size parameter. We want the worktop to scale with the Y axis to match the cabinets, though typically it would also overhang slightly, so we need to adjust the global Y size numeric node with another offset parameter. And to do this, wire a new arithmetic node to the Y fixed size input of the transform node. Wire the Y fixed size numeric node to the first input of the arithmetic operator. Then create a new numeric node, change the type to scene units, and wire it to the second input of the arithmetic node. Now if you adjust this property from the modify panel, you'll see that you can change the width of the worktop relative to the depth of the cabinets. So far so good, so next up, let's add the doors. This is perhaps the trickiest step, because it includes a few conditions and has some padding tricks which can be harder to understand. The segments and the selector operators have already been added, and the selector operators are used to change the geometry based on the material ID of the underlying spline. To enable this mode though, all you need to do is change the selector dropdown to spline material ID, as you can see here, and that's it. To get started with the rest of this part of the style, we can duplicate again the existing L1S generator and detach any existing segments from the inputs. This time though, change the mode to count and set the count value to 1. This works similarly to the scale mode, but I've found it's more reliable for this style in my tests. So first off, we'll combine the three sections back into a single door. As we've seen in the demo at the beginning of this tutorial, these are created from three segments, a left, a right and a default. The two sides shouldn't scale, but the middle will. We'll need to create a calculation that finds the size of the middle section based on the length of the spline minus the two sides of the door, the carcass and any padding that we want to add. To do this though, we'll start with the compose operator and attach it to the default input. This will allow us to combine the three segments into one unit. Next, we'll create two conditional nodes and one transform node. Wire one conditional node to the first input of the compose node, and then add the transform node, and then finally add the other conditional node. These conditional nodes will be used to detect what type of vertex is used just before the spline section. As we've seen, this changes the side door hangs from. Whereas the transform node will be used to rescale the middle section to fill in the gap that's left. To set up the conditional node, turn on vertex type and set the vertex type dropdown to corner. So wire the door left selector operator to the first conditional node's true input, and then wire the door left selector operator to the second conditional node's false input, but via a mirror operator. Then wire the door right selector operator to the second conditional node's true input, and then wire the door right selector operator to the first conditional node's false input, but again via a mirror operator. And we've now set up some conditions that swap the geometry based on the vertex type. Now let's scale the middle part of the door. Select a transform node and export X fixed size. Wire the door default selector operator to this input. To calculate the size, it's time for some maths. We need to take the length of the spline section and then deduct the size of the left side, the size of the right side, the size of the frame, and any padding. Because we need to use the sum of the padding and the frame size for another calculation in a second, we'll create a node for this separately. To do this, create an arithmetic operator and attach the door padding numeric node and the X size of the frame carcass sides. Now you know why we exported it earlier. Then export the X size attribute for both the left and the right selector nodes. Then create another arithmetic node and attach both these X size attributes and the arithmetic operator we just created to the inputs. Change the operation to expression and create the sum by opening the editor and entering X section length minus input 1 minus input 2 minus input 3. This gives you the space left for the middle section of the door. And you can then wire this new arithmetic node to the transform node's X fixed size input. and that's the door sizing complete. But now we need to create some padding, some gaps between the doors. To do this, create another transform operator and wire it to this generator's start, end and corner inputs. First off, we need the gap to be at least the same size as the frame or carcass, plus any additional padding. We've already created this equation just a second ago, so now we can reuse it. Right click on the transform node and export the X fixed size property, and then wire the existing arithmetic node to the newly exposed input, and that's it. All we have to do now is make sure the doors are in the correct position. At the moment, they're in the wrong place on the Z and the Y axis. So the Y axis is relatively easy. We can just export the generator's Y offset property and connect it to the Y size numeric node. But once again, let's add a bit more flexibility. We also want to be able to offset the doors from this position so that they can appear either inside the frame or on the surface. To do this, create yet another arithmetic node and wire Y size to the first input. Create another numeric node, change the mode to scene units and then name it doors offset. Wire this to the second input. And finally wire the arithmetic node to the Y offset input and the doors will be correctly placed. And then to fix the Z offset, you need to take the same value as used to place the carcass or frame sides and then add it to the padding value. Do this with another arithmetic operator and then wire the results to the Z offset property. Nearly there, only one more generator to go. So finally, what about the handles? Well, for the sides that's not a problem because we've already added them to the door segments. But for handles that are on the top or the bottom, or for example on drawers, we can't use this approach because they'll scale with the default segment and look wrong. Instead, we use another generator and add them to the evenly input with a count value of 1, which will keep them centered. Here's how. Duplicate the doors L1S generator and remove the existing segments from the inputs. In this case, the Z and the Y offset are already set correctly, so we won't need to touch those. You need to make sure this time the spline is always broken on the corners, so to do this, wire a null or empty segment to the corner input. There's one in this graph already. Change the evenly mode to count and enter a count value of 1. As mentioned, this will add one handle to the center of each spline section. As you can recall from earlier, where no centered handle is required, a null segment must be selected instead. Now wire a transform operator to the evenly input and wire the handles selector to the transform operator. Change alignment Y to top and alignment Z to pivot. This is to ensure they align correctly with the rest of the geometry. But what we haven't done yet is allowed for the thickness of the door. So to do this, export the Y fixed translation value, create an arithmetic node, set the mode to expression and enter negative input 1. Wire this to the Y fixed translation input. Finally, right click on the door default selector node and export the Y size attribute. Wire this to the arithmetic node to offset the handles the thickness of the door that's currently being selected. Congratulations, you've made it to the end, and this graph looks complicated, but really it's just about connecting sizes of segments to automatically place geometry correctly and sharing as much as possible the same parameters and driving everything parametrically. Though it might take a little time to build, I think it's worth the effort. The same principles can easily be applied to all kinds of other uses, and we now have a style where you can select cupboards based on material IDs, change the hanging direction of the doors using vertex types, control the overhang of the worktop and the depth of the plinth, change the width of the cupboards, choose door padding or even change the kitchen from frame to surface mounted, and choose whether or not to use a worktop. The calculations for all the segment sizes are based on the door segments you add, so once it's created, it's easy to change the geometry to get completely different results. In fact, even for beginners, this style is helpful because you can swap the geometry without ever having to know how the rest of the graph really works. So until next time, stay tuned for future tutorials, and for more information about many aspects of RailClone's features, please see our reference section or visit the tutorials page for more tips and tricks videos, as well as in-depth tutorials.